Hey everyone, this is BITSCTF, hosted by Bitskrieg, a CTF team based out of BITS Pilani, a school in India. For this video, I'll be covering 7 of the challenges. There'll be timestamp below. As always, if you have any questions, feel free to leave a comment or message me on Discord. I'm Conrad, and if there's anything I did wrong that I could have done simpler, please also let me know. I'm always looking to learn. And with that, let's get started. The first challenge is baby-rev by Arman. It says Anita Max Win, and we're given one download file. The download file is an ELF file, so we can load it up in Ghidra. If we look, it's going to ask us for a string, then it's going to read the string, it's going to compute the string length. If the length is equal to 0x18, it's going to call myfunc, and then within myfunc, it's going to compare character by character. And if we get all those correct, it says yippee. So all we have to do is copy this out. We can dump it into a text editor, and then from there you just need to massage it so that you can read it off a little bit easier. When you're done, it'll look something like this. One thing to make it a little bit easier to do the sorting is if you hold Alt in Visual Studio Code, you can move a line up and down. And so once it's all clean, you just move the lines in the correct order and you're done. Yeah, and from there, the flag says BITSCTF, welcome to Rev. The next challenge is baby-rsa. It says RSA is for babies, so we improved it by taking it to the next dimension. We're given a download Sage file and an output file. This challenge, we're doing RSA, but instead of taking a number and raising it to a power, we're taking a matrix and raising it to a power. So it's going to generate a random key. It's going to take some plaintext, which is the flag, and it's going to split it into 4 equal parts. Then it's going to put that in a matrix. So we're using Sage. So this is Sage. We're doing it over Zmod. So everything is going to be modulus n, which is just p times q. And these are our 4 chunks of plaintext. And then here's the encryption function. So it's just g raised to the power of 65537. We're in Sage, so this is to the power of not XOR. So we're going to take our message, we're going to encrypt it, we get out our ciphertext, and then it's going to print out the ciphertext chunks. So here's our n, and here are all the different chunks. And then I think you can ignore that. I think the output was a little bit different. I massaged it a little bit. But basically, we're going to get these 4 outputs and an n. So I spent a bit of time thinking we were supposed to do something clever with, maybe there's a way to factor matrices or take the nth root of a matrix, but I couldn't get that working. Maybe that is the solution, but it turns out that this n doesn't look factorable in here, but apparently someone put the factors on FactorDB. So you can send it to FactorDB and you'll get out a P and a Q. I'm not sure if this was the intended solution, but it's here and it works. So if you know P and Q, obviously RSA is broken. One thing that's a little bit different about this matrix scheme, though, is to calculate the decryption key. Normally we do like the inverse mod and from phi, and phi is P minus 1, Q minus 1. For some reason, if it's a matrix, you're supposed to use this phi, or it's p squared minus 1, p squared minus p, q squared minus 1, q squared minus q. It was mentioned in this paper. I don't know why. I think that's for smart people. But it was mentioned in here, and once I did it, it worked. So I'm not really sure why the phi is different. They kind of explain it. Something about general linear groups and stuff, but yeah, I didn't understand it. But anyways, it works. So we can use that phi, and then we can calculate the inverse of our encryption key. We'll get our decryption key, and then from there, we just take our matrix. And to generate the matrix, you just take all the values. You just do the same thing. It's all Sage. So we're going to calculate g to the d, then we're going to grab the plaintext from it. We're going to grab it from byte. We do lift because technically I think it's in a field or a ring, and we want it to be part of the integers so that we can grab out the values. I think you can convert it to a string to an int, but when I just converted it to an int for some reason, it was mad. I don't know why. But if we lift it into the integers, then Sage and Python play better together. But anyways, we grab out the plaintext from all of them, and we print it out. So we can run this in Sage. I already did it there, but I'll rerun it, and we get the flag. BITSCTF, general linear group, can do anything. So, fun. The next challenge is the not suspicious agency, so the NSA. It says the NSA has created a very secure way to encrypt your messages that only trusted individuals can decrypt. Trust is very important after all, and we're given 3 download files. So this is probably my favorite challenge from the CTF, just because I've known about this exploit. I've just never actually done it, so it's fun to finally do it. If you're not familiar, the NSA created some algorithm called the dual EC DRBG, and they published it, and I think they tried to get it integrated into NIST as an official standard, and I think it was accepted as a standard. But I think most cryptographers believe that it has a backdoor, and so no one actually uses it. And people believe it has a backdoor because these points were just given for no particular reason. Normally, I think when you give points for this scheme, you're supposed to take like a hash of some message. So there's no way that these points have a relationship. But the NSA did not give any reason why they picked particular points, and so I just believe that there's a backdoor. And so we're going to be pretending that we're going to be exploiting the backdoor. Again, we don't know what the real backdoor is, but this is a fake scenario where we have a fake backdoor. So that's kind of the background. So you can kind of read about this exploit and figure everything out, and then from here it's just an implementation detail to actually run it. But the way this works, so it's a random number generator using elliptic curves, and after it generates a bunch of random numbers using the elliptic curve, it's just going to do an XOR, and from there we can encrypt stuff, and then we need to decrypt it. So overall, the challenge, the way it's going to work is it's going to have this generator, which is the elliptic curve random number generator, and it's going to encrypt this message. So we have some plain text. Keyly, this is over 30 bytes or 32 bytes, which makes it a little bit easier for us, which we'll talk about. And then we're given the ciphertext for the encrypted flag. And this should be all we need. The way the algorithm works is we're going to start with a initial state, and it's just going to be S, and it's going to be 16 random bytes. And then from there, we're going to call this generator over and over. For the algorithm to work, it requires 2 points, which are called P and Q. So these are chosen by the implementation. And so these are the values that were given that are backdoored. And what's going to do is, so this is just elliptic curve stuff. We're going to take this, so S is just a number, and we're going to multiply it by a point P. So, we're doing elliptic curve math. So, P is just going to be, multiplied and going to bounce all over this curve. And so remember, it's kind of a one-way function. We can multiply a number, but we can't really divide a number without like guessing and checking, or there's a couple algorithms that are a little bit better, but basically guessing and checking. So it's pretty much one way. So we're doing S times P. And we're calculate this R, and then the value we return, so this is a random number generator, we're going to return R times Q, except for the top 2 bytes, which is a implementation detail from this random number generator. And then the new internal state is going to be equal to R times P. So like I said, the reason there's a backdoor is because, or it's believed that there should not be a relationship between P and Q. These should be 2 very random points, and so that you can't kind of move in between them. Like knowing the output of the random number generator should give you no information about the internal state. But if you know a relation between P and Q, it's possible to figure out the internal state. And once you know the internal state of a random number generator, obviously you can predict, the rest of the numbers in the sequence. And so that was pretty much the challenge. Like I said, this is what they're going to give us. They're going to give us the P and the Q. They give us the ciphertext for the known plain text, which was, this is a test string for debugging, and they give us the ciphertext for the flag. So this is the solve file, all written in Sage. First thing we had to do was figure out what curve they're working on. I just assumed that they were going to be working on the official NSA curve, and it happens it was the case, and there's a way we can test that, which I'll show in a second. So I just grabbed those parameters off from online somewhere. So we need the P, the A, and the B, and so then I just put this into a Sage elliptic curve, and everything just works nice and pretty. These are the 2 these are the 2 points that were given to us as part of the challenge, and there was also a file called backdoor, and it had this value. I didn't describe what this was, but we can test it because we're guessing it's based off of this NSA thing. If point P times the backdoor is equal to Q, then we know we're on the right curve and we know what sort of attack we're going to do. And thankfully, this did end up being true. The backdoor times P is equal to Q, so there's a relationship between P and Q, which there really shouldn't be, but there is, so that means we can exploit the system. So I copied out the encrypt function, the generate function. Obviously, I had some print statements in there. You can ignore this. This was me testing, more testing. I copied out the 2 different ciphertext and the plain text. So step 1 is we need to figure out the output of the generate function. So the generate function, this yield from, is actually pretty interesting. So when you do yield from, I guess it returns byte by byte this output. And so when we get byte by byte from this output, it's going to go to this encrypt function and it's going to encrypt byte by byte by the message. Since we know what the plaintext is for the first message, and it's just an XOR, we can figure out what this value is right here. Because we're just going to read it byte by byte. Technically, it's only 30 bytes because it chops off the first 2 bytes out of 32. So we can figure out what the first 30 bytes are, depending on your order. So we'll have 30 bytes. And what we do to do that, we just take the XOR of the plaintext and the ciphertext, and we'll get out that value. Like I said, the top 2 bytes are chopped off for some reason. So we need to determine what those 2 bytes are. So to do that, I went from 0 to the full range of 2 bytes. And basically, I'm just going to guess what these top 2 bytes are and append them. To kind of check if it's correct, first we can ask, is this X value on a curve? If it's not, we know we have a wrong value and we can continue. If it is, then we continue with the attack. I just try the attack on every possible value, and if it works, we win. So the way the attack works, really, if you just sit down with pencil and paper and do the math, it's really not too bad. But if we look here, I'm just going to draw it out. R is equal to S times P. So that's this line right here. And let's actually call this S0. And then the output is equal to R times Q. But this is equal to R, which is S0, times P times Q. But we know that there's a backdoor. And so Q is not actually equal to Q. It's actually equal to times P is times backdoor times P, which is interesting. And then the S1 is equal to R times P, where R is equal to S0 times P. Cool. So really, I mean, if we could get S0, that'd be great. I don't think we can. Maybe we can. I don't know. But we can easily get S1. And so we know what this value is because this is the output right here. And so we can calculate most of this stuff. But what we're actually going to do is we're going to take this value and we're going to multiply it by the output. Sorry, we're going to take output and we're going to multiply it by the backdoor inverse, which you might have saw that I calculated up here. So to calculate this inverse value, since we're dealing with like fields and stuff, you need to do the inverse, not just a simple division. So mod inverse is just backdoor and n. If we multiply by backdoor inverse, we're going to get S0 times P times P. So we're just dividing by backdoor, but it's mod inverse because we're dealing with the field. And once we have this, this is an interesting value because this is the next internal state. So all we have to do is figure out what the output of this is, which is not too bad. It's just an XOR. We figure out the missing 2 top bytes, then we multiply it by the backdoor. Very simple, and we get the internal state. Once we know S1, that's pretty much game over. We know all the future outputs of this random number generator, and so after it generates our fake, plaintext message, this is a test string for debugging. It's going to encrypt the flag, and we know what the random values are, so we can reverse the XOR and we get the flag. Again, so that's the description of the attack. And to actually implement it, like I said, we're going to take our guess point. It's just, like I said, I'm adding on the top 2 bytes along with the base. I'm going to take it, multiply it by the backdoor inverse. You might see these all these array indexes. I'm just grabbing the X value out of the elliptic curve points. From there, I'm going to construct a new generator now that I know the internal state. Instead of starting at S0, I'm just going to start at S1. And then from there, I'm going to generate a bunch of keys, the output. To get the output, you just call next on the generator. And we're only doing it byte by byte, so I just grab the low byte. And then from there, I just XOR the key stream. So this is the output of our random number generator with our ciphertext. We have to start at the 5th byte just because this is 35 bytes long and we only use 30 bytes of random number generator. So the last 5 bytes are going to belong to the 2nd cycle of the random number generator. So we just scoot forward by 5 bytes. And then to check and make sure we actually had the correct value, I just see if bits is in the output. And if it is, we probably had the flag. So we can run this, nothing too exciting, but let's start up Sage. Let's dump it in there. Oh, it doesn't want our math. And it's thinking. My computer's much slower when I'm recording. There we go. BITSCTF, never blindly trust standards. So, fun challenge. The next challenge is osint ladylove by Kriti. For this challenge, we're going to be given this stolen painting, and we're supposed to find a female that was at this place. And apparently, this guy loves this female, so maybe she's pretty or something. And we were given a hint. The hint helped a lot. It said that this person's birthday was on the 16th of February, 1913, if she were still alive. Cool. So this female was born on this date, and she has some resemblance to this painting. And we can open up the painting. And it is this. So first thing you can do is you can take this over to Google Image. If you give it to Google Images or Google Lens, it'll correctly identify the painting. And the painting, it's this one right here. So you can just Google around for it. And so this painting was done by Peter Adolf Hall. You can read about the painting here, and it says when he was in Spa. So this painting is of the city Spa, Belgium. Cool. Which is this. Cool. So from there, we can just start Googling. We know we're looking for Spa, Belgium. Something to do with February 16th because it's that lady's birthday. There are a bunch of stuff pops up on Google's which we don't care about. Some F1 race, some weather, some thermal stuff, some hotels. Eventually, a Wikipedia article pops up for Carmen Hallis Isi. She was a Miss Universe, something to do with Spa, Belgium. So that's good. And if you keep going around, eventually you'll find out her birthday was like February 16th or something like that. Oh yeah, February 16th, 1913. So the dates match. And for the challenge, we're supposed to, the answer is the meaning of the loved lady's last name. That's a little strange. What is the meaning of her last name? It's Isi, but if you scroll down, where is it? Oops. Blah, 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 gave her the family name Isi, which means queen. So the flag was just queen, if you wrap it in a BITSCTF. So pretty fun challenge. The next challenge is PONE, mogambro-certainty-principle. It was by PAMD, and we're given a netcat port, something to do with time and precision. So this wasn't actually a PONE challenge. This was just a programming challenge. So if we netcat to the port, it's going to ask us for a password. We can say hello or just hi. It says incorrect password, and it gives us the amount of time that was taken. So this is just kind of like a timing leak, password breaking sort of challenge. If I type in the first one, we'll see that. Oh, actually, it'll just tell us what it is. Let me do most of it. If we go like most of the way, we can see this timing took like 10 to the minus 5, whereas this one took, this guess took us 1.15 seconds. So the way this challenge worked is we have to enter in, I guess, 5 different passwords, and each one of them has a timing leak, but it's progressively slower, or faster, I guess. So if we start again with the first one, the first letter is S, so I'm going to do SA. We can see it took 0.1 seconds instead of 10 to the minus 05. So every correct character adds a 0.1 second to the comparison. So obviously very stretched out. Character comparison is not that slow. But from there, I mean, it's just go through every single character. When the character adds on 0.1 seconds, I think it went from like 0.1 to 0.05 to 0.025 to 0.03 or something like that. It's pretty obvious when you look at the response with how long the delay, the program delay is. You just go through, construct all of them, and when you're done, it'll give you the flag. Yeah, so if we type in the flag, we'll do this. The first one was this one. They're kind of inappropriate, which is, I think, a theme for this CTF. Type in the next one and the very last one. That was probably poop. I'll do it again. Yeah, I think I forgot it was a P. This challenge took like 3-4 hours, I think, just because the internet was very slow for a while. We're in Colorado and we just don't have good internet right now. But here's the flag. It says BITSCTF, congratulations on the successful entry. So fun. The next challenge is access granted. It says first things first, Mogambro is so dumb that he might be using the same passwords everywhere. So let's crack his PC password and then wrap the password in BITSCTF. Cool. So for this challenge, we're going to use volatility. So they just give us a memory dump. You just use volatility. You ask for all the passwords or the hashes. Volatility will do all the heavy lifting for us. Volatility 2 wasn't working for some reason, so I switched to Volatility 3. I have both installed. Sometimes one works, sometimes the other one works. But we can see we get a bunch of users and their hashes. So we take this one, we're going to cat it into just a hashes file, and then we can run hashcat on it. So we're doing NT hash cracking, NTLM, I think, hash cracking. So hashcat-m, which is the hash version for it. Then we're cracking hashes, and we're going to pass it a dictionary, opt-raw-q. Already cracked it, so we're going to show it. I'm just not going to say that. Cool. The next challenge is 0.69 day. It's going to give us a bunch of stuff. Basically, we need to figure out the CVE that was used to get a foothold on the system. I think there's many ways to solve it. What I ended up doing was just doing like a process list. I did a bit of searching, but if you look at this process list, you'll see some kind of sketchy stuff here. There's notepad.exe, Chrome, conhost, and command.exe. And they're all called relatively around the same time, which is pretty interesting. And the process, the process right before that was WinRAR. So if you go to WinRAR CVE, you might find out that there was a CVE related to WinRAR. I actually was checking out this article, Google blog, because they do good research. And we can see that there's been a whole bunch of stuff with WinRAR and exploiting people with this specific CVE. So I just guessed, and this one happened to be it. So we just wrap it in the flag, and that was it.